Okay, today we get to do 3.3, which is optimization with linear programming. It sounds super fancy. It's not too bad, but you're going to want to pay close attention. So basically, it's a lot like yesterday, but I'm going to specifically care now about where it is they intersect. These are going to be the constraints. These intersecting points are going to be called vertexes, or vertices, or a vertex. And the shaded region is going to be called our feasible region. If you have a completely enclosed feasible region, like my example on the left here, that's going to be called a bounded region because it has complete boundaries. However, if you look on the right, those two side lines are parallel. Oops. There we go. Parallel. And so they're never going to intersect, which means the shaded region goes on forever. So we're going to call that unbounded, like so. So these problems are going to be quite lengthy. There won't be too many of these as homework. It'll be a shorter assignment. Let's go ahead and get started. Take this assignment in chunks. So step 1, graph it. And when I say graph it, you're going to graph all the graphs. Understand, not everything they give you is the graph. See this bottom thing, how it looks different? It's the, says f of x and y. That is not a graph. That's the function you're going to use. So kind of block that off, make it separate, and graph everything on top. Now what's interesting is when they give you vertical and horizontal lines, they're going to write it like this. That is actually two separate things to graph. The first one is -2 is less than or equal to x, which I don't really like seeing the x on the right. So if I rewrite that, that's x is greater than or equal to -2. And then the second equation, oops, I don't know why it's doing that, is x is less than or equal to 6. So basically what I have are x equals a number equations, and remember that those are going to graph to be straight vertical lines. The first one is at -2, so it's going to be a vertical line here, and it is going to be a nice solid line, extra ink, extra ink. And the other one is at 6, 1, 2, 3, 4, 5, 6, and it does get to be a nice solid line again, extra ink, extra ink. So likewise, with this one, that is two different functions to graph. The first one being 1 is less than or equal to y. And the second one, or my fourth equation, being y is less than or equal to 5. And again, I don't like the way number 3 is written, so I'm just going to switch it. Greater than or equal to 1. Okay, so that means if it's a y equals a number type equation, that is a straight horizontal line. So let's try one, a horizontal line at 1. And if I try one at 5, 1, 2, 3, 4, 5. Try that again. Where was it? Here it is. Like so. Now one thing I've kind of neglected to do so far is to go ahead and figure out where they shade. Sometimes, I don't know, just with all the arrows, I find it easier to wait on that. So I'm going to go ahead and graph my last line. That is this one right here. Don't forget that one needs graphed yet. That's actually equation number 5 today. So up 3, 1, 2, 3, put a point, and it looks like it's 1 over 1. So up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, all the way across the graph. Down 1 over 1, down 1 over 1, down 1 left 1. All right, now I can make a nice straight line based off of that. Like so. Okay, so now I'm going to go back. The good news is none of these lines go through 0, 0, so that should make my plugging in process much quicker. So let's just do that real quick. Is 0 bigger than -2? The answer is yes. So on my -2 line, I get to shade towards 0, 0. Notice again, I'm just using the little arrows. Is 0 smaller than 6? The answer is yes. So my 6 line gets to shade to the left. Is 0 bigger than 1? The answer is no, so shade away from 0. Is 0 smaller than 5? The answer is yes, so it shades down. And last but not least, I'm going to have to do this one all the way up here. Kind of running out of room here. 0 is less than or equal to 0 plus 3. And so is 0 smaller than 3? And the answer is yes. So I do get to shade down. So now comes the fun part of figuring out where is the shaded region. It should be in between these two lines, it looks like. In between these two lines. So that kind of gives me this box to look at so far. And then finally, so I'm trying to decide, is it this side or this side? And because this line shades that way, I'm going to decide that it shades in here. And here we go. Believe it or not, that was step 1. Kind of a long one, wasn't it? All right, so now we get to do step 2. Actually, step 2 is going to be list the vertices. What are the vertices? The vertices are all the corners of your shape. So in my case, I see a vertex here, 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 and here. This one is not one because it isn't a corner to my shaded region. So list those vertices. The first one is at what? Negative, and it doesn't matter what order you do it in. So what? -2, 1. What is that one? 2, 5? 1, 2, 3, 4, 5, 6, 6, 5. And what? 6, 1. Okay. Step 3. Plug those points into that function. So, if I plug in -2, 1, that's going to be -5, my x is -2, plus 2 times 1. Can we do some mental math here? -5 times -2 is a positive 10, plus 2 is 12. -5, 2, plus 2 times 5. All right. -10 plus 10 is 0. -5 times 6 plus 2 times 5 is -30 plus 10. Whoa! What happened there, marker? That's -20, correct? And last but not... Oh. Yeah. Last but not least is -5 times 6 plus 2 times 1, -30 plus 2, which is -28. Whew! Feeling exhausted yet? Okay, finally, step 4. Oh, what's going on? There we go. List the minimum and maximum. This is the last and final step. So here's what I need you to do. Come back up here and circle out of 12, 0, -20, and -28. What's the biggest number? Biggest number is 12. That's your max. The smallest number, -28, that's your min. So I'm going to list those 2 points. The max is at negative 2, 1. And the minimum, by the way, I might list that maximum as 12. The minimum is negative 28. And that happened at 6, 1. So that's what you're going to do for those. When it comes to the minimum and maximum ones, I'm going to kind of just skip ahead here to where it's all graphed them for a moment here. So give me just a second. It's going to be something more or less like this. It's not perfect, give or take. These are supposed to be parallel lines. Again, this is a guesstimate of what it's supposed to be. I do already know by the time I get to step 2 where I'm supposed to write down what are those points. The points are supposed to be negative 4, 8, and 2, 8. So I was kind of close. But here's the problem. This one I can see is unbounded. So if you find yourself with an unbounded, you need to pick a point to use as a test. And I like to use a point that's like way, way, way far away. Nothing close up here. Choose it far away from your other points. So like maybe like 6, negative 1. Maybe we'll try that. Okay, so now I'm going to go ahead and plug all of those in. And I'm going to go ahead and maybe help us out on time here. I promised you when you plug in negative 4, 8, you're going to get 88. And I promise you when you plug in 2, 8, you're going to get 52. I'm just plugging in right here to get those. I need to plug in 6, negative 1, because I don't know what that one is. So negative 6 times my 6 plus 8 times my negative 1 is negative 36 minus 8, which is what, negative 44? Okay, so if I was only looking at the points up here, right, I would be calling this one my maximum and this one my minimum. What you need to do is look at your random point and see which rule it breaks. And it looks like it's going to break the rule of being a minimum, which means there is no minimum. Okay. On this specific case, I could have just looked at it and seen there was no minimum, but it is going to do weird things to you. Depending on what negatives or whatever it puts up here at you, it might do funky things and it might have no maximum. So just watch out that you make sure you plug one in. So my answer on this one would be my maximum is at negative 4, 8, and it equals 88. No minimum.